Good morning, distinguished guests, fellow researchers, and industry colleagues. It is a great honor to stand before you today at the International Conference on Digital Technology-Driven Engineering 2025. My name is Dehan Yao, and I am here representing the China Construction 6th Engineering Bureau Corporation. Today, I wanted to talk to you about the intersection of two very different worlds, the rugged, physical reality of civil engineering and the precise, data-driven world of artificial intelligence. Specifically, I will be presenting our research on a helmet and reflective vest recognition system based on the improved YOLOv11 algorithm. We are living in an era where digital transformation is reshaping every industry, and construction is no exception. However, despite our advancements in building materials and structural design, one fundamental challenge remains: worker safety. The construction industry is widely recognized as one of the most hazardous sectors in the global economy. On any given day, a construction site is a dynamic, complex environment filled with heavy machinery, moving parts, and significant risks. In this environment, safety compliance is not just a regulatory checkbox. It is quite literally a matter of life and death. We know that personal protective equipment, or PPE, specifically safety helmets and reflective vests, is the first line of defense for our workers. Yet, ensuring that every worker is wearing this equipment at all times is a massive logistical challenge. Historically, we have relied on manual monitoring. We rely on safety officers walking the site, checking for compliance. But safety officers cannot be everywhere at once. Manual monitoring is inefficient, it is costly, and unfortunately, it is prone to human error and fatigue. This is where our research begins. We asked ourselves, can we build a system that never sleeps, never gets tired, and can see what the human eye might miss? Can we develop a highly accurate, real-time automated system to ensure worker safety by detecting mandatory PPE? To answer this, we turn to the field of computer vision, specifically the YOLO, or You Only Look Once, family of algorithms. Since its introduction in 2015, YOLO has revolutionized object detection by treating it as a single regression problem, allowing for incredible speed and real-time performance. Over the last decade, we have seen this technology evolve from the original YOLOv11 to the sophistication anchor-free YOLOv8 in 2023. However, 2024 marked a significant turning point in this technology's history, a moment we might call a fork in the architectural road. The development of YOLO split into two distinct philosophies. On one side, we saw YOLOv10, which pursued what we might call academic purity. It eliminated non-maximum suppression to create a pure end-to-end architecture. It was a theoretical breakthrough. But on the other side, we had YOLOv11. This model represented the path of engineering pragmatism. Developed by the Ultralytics team, it focused on module-level optimization and practical adaptability. For us, operating in the harsh reality of a construction site, theoretical purity is less important than verifiable stability and accuracy. Therefore, we chose YOLOv11 as our baseline, because in engineering, what matters most is what works reliably in the field. Yet, even a state-of-the-art model like YOLOv11 faces what we call the final mile problem. When you take a model trained in a lab and deploy it on a construction site, performance often drops. We identified three specific barriers that cause standard models to fail in our industry. First, we have the problem of small target sizes. Construction sites are massive. Surveillance cameras are often placed high up or far away to capture a wide view. This means the workers in the video feed appear tiny. Resolving a helmet or a vest on a figure that is only a few pixels tall is incredibly difficult for standard algorithms. Second, we deal with low image resolution. We're not filming movies on site. We are using industrial CCTV. The video streams are often compressed, blurry, or suffering from motion artifacts. This lack of clarity reduces the feature details that AI needs to make a decision. Third, and perhaps most challenging, is occlusion and complex backgrounds. A construction site is cluttered. There is scaffolding, steel bars, heavy trucks, and piles of materials. Workers are constantly moving behind these objects. A standard model might see a worker from the waist up and fail to detect the vest because it is partially hidden by a steel beam. Our research is a direct response to these three challenges. We did not just apply YOLOv11, we fundamentally improved it to survive in this environment. Our methodology began with the foundation of any good AI, the data. To address the specific visual characteristics of our sites, we compiled a specialized dataset of 22,453 images. Now, annotating over 20,000 images by hand is a slow and expensive process, so we innovated here as well. We employed a self-supervised learning technique. We trained an initial YOLOv11 network on a small, high-quality sample to act as a teacher model. This teacher then automatically annotated the rest of the massive dataset. This approach allowed us to rapidly build a high-fidelity training set that covers diverse construction environments, from open excavation sites to cluttered interiors. With our data ready, we moved to architectural innovation. We introduced two major modifications to the standard YOLOv11 structure. Our first innovation was designed to sharpen the model's focus. We integrated the convolutional block attention module, or CBAM, into the backbone network. You can think of this as giving the AI the ability to focus like a human does. When we look at a scene, we don't process every pixel with equal importance. We focus on the relevant details. CBAM allows the model to do exactly this through two simultaneous processes. First, it uses channel attention, which decides what features are important. For example, learning that the specific yellow color and smooth texture of a helmet are critical signals. Second, it uses spatial attention, which focuses on where that information is located in the frame. By refining features along these two dimensions, the model becomes much better at amplifying the signal of the PPE while suppressing the noise of the complex background. This was our solution to the problem of small and occluded targets. Our second innovation addressed the training process itself. Standard object detection models often use a loss function called CIOU. The issue with CIOU in our context is that it can be negatively impacted by low-quality training examples, for instance, anchor boxes that don't quite overlap with the target. In a messy dataset from a construction site, these poor examples can confuse the model and hurt its ability to generalize. To fix this, we replaced the standard function with the YZIOU loss function. This function incorporates a dynamic, non-monotonic focusing mechanism. In plain English, this means the system is smart enough to assess the quality of an example during training. It intelligently downweights the loss from low-quality, confusing examples and prioritizes learning from high-quality, clear examples. It effectively tells the model, don't worry about the confusing, blurry data. Focus on learning from the clear data first. This strategy significantly improved the model's overall detection accuracy and its robustness in challenging conditions. So, what were the results of these efforts? Did these innovations translate to real-world improvements? The data shows a resounding yes. We rigorously evaluated our improved model against the baseline YOLOv11 on our specialized test dataset. The baseline model achieved a mean average precision null map of 87.3%. Our enhanced model, armed with CBAM and YSIOU, achieved a map of 92.3%. That is an absolute improvement of 5.0%. In the world of object detection, where researchers often fight for fractions of a percentage point, a 5% leap is substantial. It validates that our approach didn't just tweak the system. It fundamentally solved the final mile problems we identified. To visualize this, imagine a wide shot of an excavation site. In our tests, the baseline model would frequently miss a worker standing in the distance, or it would put a low confidence box around a vest that was partially blocked by a truck. The baseline might say, I think that's a vest, but I'm only 45% sure. Our enhanced model, looking at the exact same image, detects a distant helmet that the baseline missed entirely. And for that partially blocked vest, it identifies it with high confidence. This difference between a missed detection and a high confidence identification is the difference between a safe site and a potential accident. Finally, we must consider the practical side of engineering, deployment. A model that is 100% accurate but takes 10 seconds to process an image is useless for real-time safety monitoring. We needed high accuracy in a lightweight package. We are proud to report that our algorithm successfully achieved this balance. While we added complex attention mechanisms, the model size increased only marginally, from 3.68 megabytes to 4.49 megabytes. This is still incredibly small enough to sit on a modest edge computing chip. In terms of speed, we achieved an inference rate of 62 frames per second. While this is slightly lower than the baseline's 79 FPS, it is well above the 30 FPS threshold required for real-time video. This means our system is ideally suited for deployment on platforms with limited computational resources, such as NVIDIA Jetson modules or even smart cameras installed directly on the construction site. We have achieved high-fidelity safety monitoring without the need for massive, expensive server racks. In conclusion, our research provides a robust, deployable solution for real-world safety monitoring. By developing a specialized dataset, enhancing the YOLOv11 backbone with the CBAM attention mechanism, and improving training generalization with the YSIOU loss function, we have created a system that is both accurate and efficient. We believe that this work provides a direct path toward more reliable and scalable automated safety compliance. It moves us one step closer to the ultimate goal of intelligent construction. A worksite where digital technology acts as a guardian, ensuring that every worker returns home safely at the end of the day. Thank you very much for your time and attention.